Ladies and gentlemen, it's time to classify real numbers. Now, it's one of the beginning topics in my 8th grade math curriculum. Now, across the country, the United States, depending on if you live here, maybe you're on the other side of the globe, you might see it in 7th grade, 9th grade. I don't know where you would see it, across the globe. But primarily, I see it around 8th grade, 7th, 9th, just depending, again, on your state. Okay, now, before we get into actually classifying real numbers, I just want to address something quickly to not only the students, but the parents. Not necessarily even directing it towards my students or the parents of my students, but just in general as a whole. I love math. And I know not everybody can say that, and that's okay. Okay. I'm not expecting you to love math. Okay. I'm not putting these videos out here just for the fun of it. Okay. I want you to feel successful in the classroom. I want you to feel successful outside of the classroom. I don't want you to sit in class feeling dumb that you can't do this. In my description of my bio on YouTube, it says anyone can be great at math, but you need to actually put the work in. Do you want to know how to problem solve? Do you want to be able to do deductive reasoning? I want you to have those skills outside of math. I just want you to have them in general, and it starts in the classroom. And I think social media, portrays this image that education isn't important. It's one of the most important things that we have in this society is being educated, getting smarter each and every day. And I think it starts especially in the math classroom. It's either you know it or you don't. So let's talk about classifying real numbers, but I want you to kind of think about that a little bit. You know, as a parent, as a student, I just want you to simply try your best. Okay? Not every topic's going to hit you. Okay? Not every topic you're going to be like, "Wow, that went right over my head." And that's okay. But that's not an excuse to not try. Right? So let's go ahead and talk about classifying real numbers. Now, your teacher, okay, I specifically show the one that has the squares. I'm going to pop it up on the screen here. But sometimes you might see circles as well. This is the nested Venn diagram that you see when classifying real numbers. Now, all that means nested Venn diagram, it's like a box inside of a box. Okay, and I'll explain more of why it's set up that way when we go ahead and look at some examples. Okay, but I want you to realize that you could see it a couple different ways. Circles, rectangles, or squares. Okay, and I just put the question marks here because these are all the different classifications that you're going to need to know. So let's go ahead, take a look at examples, right? I want you to think about what I said a little bit. I hope it kind of hit home maybe with some of you, and let's get into it.
I've been thinking that I can't quite get enough time on the inside of the cycle that you spin with gravity and...
Now here's this nested Venn diagram I just showed you a little bit ago. I filled in all of the question marks with all of the vocabulary that we're going to need to know in order to classify a number to its most specific category possible. And I want to make sure that you have an all-in-one stop here. I want you to know the vocabulary inside and out. I want you to see all the different types of examples of how to place these properly in its most specific subset. So this video is going to be pretty lengthy, and I'm okay with that because I want you to not have to go watch 5 other videos before you see all the different types of examples. So let's go ahead and start by classifying, well, what even is a real number? It's basically any number that you talk about with anybody. The only numbers that are excluded are things like imaginary numbers. Well, if it's imaginary, then it's not real. It's like telling people that you just saw a unicorn the other day. That doesn't make any sense. Someone's going to look at you like you're nuts. Imaginary numbers are excluded and complex numbers are excluded. Everything else is deemed as a real number. It's anything that can be plotted on a number line. So that's what I'm going to write in this real box here on the right side. Any number, I'm just going to abbreviate it with a hashtag, any number plotted on a number line. Now, once you determine if it's a real number, which again, 99.9% of the time you're working with a real number, unless you see like an I or a complex number where it's A plus BI and you got numbers written in there, okay? You'll talk about imaginary numbers in high school. We don't talk about imaginary numbers in middle school or anything like that, okay? Then you're going to get broken down into 2 main families. So you're going to notice that you're getting a little bit further inside this nested Venn diagram. So real is the most broad, you could call it. Then you want to see, well, can you classify it a little bit further? And it's going to fall into one of these 2 families, rational or irrational. Irrational, all that means is that you can't write it as a fraction. So irrational is cannot be written as a fraction. Whereas rational is the exact opposite. It can be written as a fraction. as a fraction. And you're going to notice why these are basically two separate families. It's either you can be written as a fraction or you can't. And if you can't be written as a fraction, you're going to notice it's kind of off on its own little island here. There's no other squares inside of this irrational box. If it's irrational, that's it. And you can't go any further in the classification system. So things that are irrational are things like pi, for example. Pi is the most famous irrational number that we have. It's 3.141592655, and it goes on forever and ever and ever. It doesn't stop or terminate, and it doesn't repeat. How are you going to write a decimal that goes on forever as a fraction? Well, you can't. So if you see anything that has pi in it, you should know immediately that it's irrational and it's real. Those are the only two classifications that it possibly has, and the most specific category you can give it is that it's irrational. Another example of an irrational number would be something like a non-perfect square. So let's say we had the square root of 17. If you took the square root of 17 and just punch it into a calculator, you're going to get a decimal that doesn't stop and it doesn't repeat. It's just a mishmash of random numbers. Well, again, you can't write that as a fraction, meaning that it's irrational and it's real. The most specific subset you can give it, though, is irrational. And you might also see something very simple like this. Negative 12.1478, and then you just see a dot, dot, dot at the end. That's signifying that this is going to go on forever, and there's no indication that there's any numbers repeating. Well, I would deem that as irrational. So those are the different types that you'll see for irrational numbers, but remember, irrational numbers are still real numbers. Now let's go ahead and take a look at the other side of things, which is they can be written as a fraction, which means they're rational, and there's a lot of different types of rational numbers. For example, you could have a simple fraction like 13 over 20. Well, that's already written as a fraction, meaning it's rational. You could also have a terminating decimal, something like 0.7, where it stops after the 7. Well, 0.7 can be converted into a fraction by simply saying that it's 7/10. So terminating decimals are rational. You also have repeating decimals that are rational. So something like 4.32, and you have a bar over the 3 and the 2, signifying that the 32 is repeating over and over and over again. And if you're not sure how to convert a repeating decimal into a fraction, I do have a video on the channel that shows you how to convert that to a fraction. So repeating decimals are also considered rational. Another example of rational numbers are things like perfect squares. So a perfect square would be something like the square root of 49. Well, the square root of 49 is 7. Well, 7's not a fraction, but can't you make 7 into a fraction by simply putting it over 1? So perfect squares are considered rational. You could also have something like just the number 7. Well, 7 can be written as a fraction by putting it over 1. You could have something like negative 15. Well, that's considered rational because you can put it over 1. These are all of the different types that you can see that are considered rational because they can be made into a fraction. Now, once you determine if it's rational or irrational, if it's rational, you then can classify it a little bit more. You're going to notice that there's 3 more boxes further inside this nested Venn diagram than just being rational. So the definitions get a little bit more specific to see, well, what is the best classification this number can belong to? So now let's go ahead and talk about integers. Integers can be anything involving 0, all of the positive numbers, so 1, 2, 3, 4, and so on and so forth. And it's also going to include all of those positive numbers opposites, which are all the negative numbers. So we have -1, -2, -3, -4, and it goes on forever and ever the other direction as well. But notice if you want to classify it as an integer, there's no decimals in this, there's no fractions in this. It's just numbers not involving any decimal point, no fraction whatsoever, just 0, all the positives, all the negatives. So integers, you would see something like -10 is considered an integer, or 3 is an integer, 0 is an integer, but you're not going to see a decimal in here at all. You're not going to see a fraction in here at all. However, there is one specific scenario that screws people up all the time, which is something like 15 over 3, and it's purposely done just to screw you up. What does 15 over 3 actually equal? What's 15 divided by 3? Isn't that 5? Well, that's an integer. Those are the ones that trip people up all the time. So you want to make sure that you simplify anything that you see that definitely can be simplified. Now let's go ahead and get a little bit more specific and get further into this classification system. And let's move down to whole numbers now. So whole numbers include 0, and all of the positive numbers. Notice how the negative numbers are removed now when we're talking about whole numbers. So whole numbers could be things like obviously 0, we could have 10, or we could get something like 18 over 9, which is 2, and that's considered a whole number. And then finally, the most specific category that you can get to, or the most specific subset, or the one that's the furthest inside, is the natural numbers. And the easiest way that I tell my students how to remember natural numbers is I simply want you to start counting right now. And I guarantee you started with counting by 1. You didn't go 0, 1, 2, 3, 4. You started counting 1, 2, 3, 4. You naturally start counting at the number 1. So natural numbers are considered the counting numbers. So the only thing that changes between natural and whole number is that the 0 is excluded now. And then that goes on forever and ever. So natural numbers would be something like 3, 8. Or again, if you have the one that trips you up a little bit, it could be something like 30 over 3. Well, 30 divided by 3 is just 10, when that's a natural number. So those are all of the definitions for each category or each subset in this nested Venn diagram. Now we're going to look at a ton of different examples, and I want to get down to the best classification that I could give each one of these numbers. So let's go ahead and take a look at all those examples. Now that we've discussed every category or every subset that you see in this nested Venn diagram, we can now actually go ahead and start classifying these numbers. So we're going to list every single category that each one of these numbers falls into, and then we're going to circle the word that best fits that number, or the most specific subset that that number falls into. So let's go ahead and take a look at the first one, which is the number 15. Now 15, we should all know by now that 15 is a natural counting number. If you just start counting right now, you're eventually going to hit 15. So 15, I know for sure, is a natural number. And what's nice about this Venn diagram is if you know the definition of everything, you're going to know the answer right off the bat. If 15 is a natural number, which it is, it's a natural counting number, 15 also has to be a whole number, because remember, whole numbers are just 0, 1, 2, 3, 4, and so on and so forth. So eventually you're going to hit 15. 15 is also an integer then, because remember, an integer is 0, all of the positive numbers, and all the negative numbers. And 15 then also has to be rational, because you can write 15 as a fraction by simply putting it over 1. And again, 99.9% of the time, we're talking about real numbers. 15 is also deemed as a real number, which means all of the different categories that this belongs to would be natural, whole, integer, rational. I'm just going to put RE here for real. And now to circle the most specific category that we possibly have for this is it's the furthest it can go inside your nested Venn diagram, which means 15 is going to be natural. That is the furthest subset that it could possibly go down into, meaning that natural would be the best way to classify this number. Now let's go ahead and take a look at the next one, which is negative 48. Now negative 48 is not a natural number. You're not going to naturally count to negative 48. It's also not a whole number, because whole numbers are 0, 1, 2, 3, 4, and so on and so forth. But I do know that negative 48 is an integer, because again, integers are 0, all the positives, and all the negatives. So negative 48 is an integer, which means that it fits the definition of rational, because you can write it as a fraction by putting it over 1, which means it's also then a real number. So the classifications for negative 48 would be integer, rational, and real. And the most specific subset it can go into is integer for number 2. Now let's go ahead and take a look at the third one, which is 10/11ths. Well, that's a fraction. You don't naturally just count to a fraction. It's not a whole number, It's not an integer, but it is rational. It's already written as a fraction, which is nice. So that's 10/11ths. And we know then we're dealing with a real number. So it has two categories that it falls into, which is rational and real. But the most specific category or most specific subset it falls into is that it's rational. It's written as a fraction. So that's it for number 3. For number 4, I notice right off the bat the pi symbol, meaning that this is instantaneously going to be irrational because it cannot be written as a fraction, and it also then has to be considered a real number. So the two categories that this falls into is irrational and real, but the most specific subset that it falls into is irrational for number 4. Now on to number 5. Number 5, we have the square root of 8. Well, the square root of 8 is a non-perfect square, meaning that you can't write it as a fraction. So we have another case where we have a irrational number, which is the square root of 8, but the square root of 8 is also considered real. So our two categories for this are irrational and real, but the most specific subset it can go into is irrational, and that's the best way you want to classify this non-perfect square. Now let's go ahead and take a look at number 6, which is the number 0. Well, you naturally don't start counting at 0. You start counting at 1, 2, 3. So 0 is not a natural number, but it is a whole number because, again, the definition of a whole number is 0, 1, 2, 3, 4. So if 0 is a whole number, it then is classified as an integer. It's then classified as a rational number because you can write it as a fraction by putting it over 1, and then that means it's also a real number. So what's nice is once you get good at this, if it's a whole number, it's going to meet all of the other squares that are larger than it. So if it's whole, it's going to be an integer, it's going to be rational, it's going to be real. So if you know these definitions inside and out, if you know it's natural, it's going to meet all the other definitions of whole, integer, rational, and real, which is very, very nice once you get the hang of it. You just think it's easy at that point. So for 0, this is going to be considered whole, integer, rational, and real, but the best subset to classify this under would be 0 is a whole number for number 6. Now let's go ahead and take a look at number 7. We have 3.42, and it looks like it's repeating because I see the bar over the 42. Well, you definitely don't naturally count a repeating decimal. It's not a whole number, it's not an integer, but it is rational because you can write repeating decimals as a fraction. So 3.42 with a bar over the 42 is rational, which also means that it's considered real as well. So the categories for this would be rational and real, but the most specific subset it can go into is rational for repeating decimals. Now for number 8, we have the negative square root of 81. Well, the square root of 81 is a perfect square. It's 9. So we're dealing with the number negative 9 in this case. So negative 9 is not a natural number. It's not a whole number, but negative 9 is an integer. I'm just going to write the original value, which is negative square root of 81, which again simplifies down to negative 9, which is an integer, which means then that this is also rational, and it also meets the definition of real then. So our three categories for the negative square root of 81 would be integer, rational, and real, but the most specific category or most specific subset it falls under is integer for number 8. And then we have 2 left before I have some that I want you to try out on your own in the practice session. So here's one of those ones that trips people up every single year is 15 over 3. Well, 15 divided by 3 is 5. Well, 5 is a natural counting number, which means that 5 is going to be natural, but I'm going to go ahead and erase that and just write what the original one is, which is 15 over 3, which is just 5, which means then it's going to be a whole number. It's going to be considered integer. It's rational, and it's real. So it meets all of those different categories. So we're just going to write all of those down. So we have natural, whole, integer, rational, and real. But the most specific subset that it falls under is that it's a natural counting number for number 9. And then finally, the very last one before the practice session, we have negative 17.8. Well, that's not natural. That's not a whole number. That's not an integer, but it is rational. It's a terminating decimal, which means you can write it as a fraction. So we have negative 17 and 8 tenths. And if it's rational, then it's going to be deemed as a real number as well. So the two categories for that are going to be rational and real, but the most specific subset that it falls under, though, is going to be rational. So those are the 10 questions I want to show for an example that covers basically all the different types you could possibly see. Now let's see if you can go 10 for 10 in the practice session. Now that the lesson is over, I have 10 practice problems I want you to try out on your own. I want you to get a scratch piece of paper, write down all 10 of these problems, and I want you to see if you can list every category that each number belongs to, and then circle the most specific subset for each one of them, just like we did in the lesson. So go ahead, pause the video, try out all 10 of these, and when you think you are good to go, play the video and see how you did. So I'm assuming at this point you've paused the video, you've tried out all 10, and you're ready to go over the answers. So let's go ahead and take a look at number 1. I know 0 is not a natural counting number, but it is a whole number, it's an integer, it's rational, and it's real. So you should have 4 categories listed for 0, which is whole, integer, rational, and real. But the most specific subset, or the furthest it goes inside this nested Venn diagram, is 1000% whole number for number 1. Now let's go ahead and jump over to number 2. Number 2, we have 15.9 or 15 and 9 tenths. Well, that's definitely not a natural number. It's not a whole number. It's not an integer, but it is a rational number because terminating decimals can be written into a fraction, and it's also a real number. So 2 categories for number 2, which is rational and real. And the most specific subset it falls under is 1000% the rational. And now let's go ahead and take a look at number 3. For number 3, we have 18 over 9. That's one of those tricky ones. Remember, 18 divided by 9 is just 2, and 2 is a natural counting number, which means 18 over 9 is going to fit in basically every single category except for irrational. It's natural, it's whole, it's an integer, it's rational, and it's real. So we have 5 categories: natural, whole, integer, rational, and real. And the most specific subset it belongs under is that it's a natural counting number. Now let's go ahead and take a look at number 4. Number 4 is the negative square root of 11. Well, I already know the square root of 11 is a non-perfect square, which instantly points me in the direction that it's irrational. So negative square root 11 is irrational. You can't write that as a fraction, but it is real. So we have 2 categories. So we have irrational and real, and the most specific category you can give it is irrational for number 4. Now for number 5, I know right off the bat I see a pi symbol, has to be irrational, and it is real. So again, 2 categories. So we have irrational, we have real. Most specific subset it can go under is irrational. Now let's go ahead and take a look at number 6. Number 6 is negative 7.5. 5 is repeating, so that is going to be rational because you can write repeating decimals as fractions. So negative 7.5 with a bar over the 5, and it's also real. So we have 2 categories that this repeating decimal is going to fall under. So we have rational and we have real. Most specific subset, though, is definitely 1000% going to be the rational category. And now let's move on to number 7. We have negative 55. That's not natural. That doesn't meet the definition of whole, but it does meet the definition of integer. So negative 55 is an integer, which means it has to be rational and it has to be real as well. So 3 categories. We have integer, rational, and real. Most specific subset that it's going to go under, though, is going to be integer. And for number 8, we have the square root of 36. Well, the square root of 36 simplifies to the number 6. And 6 is a natural number. It's the natural counting number. So the square root of 36 is natural. It's a whole number. It's an integer. It's rational. And it's real. So it meets 5 of the 6 categories. So we have natural, whole, integer, rational, and real. But the most specific category can go under is natural. And now we're down to the last two. If you are 8 for 8 right now, very, very nice job going into the home stretch here. So number 9, -7/13. That is a fraction, meaning it's not going to be natural, whole, or integer, but it is definitely rational. So -7/13, meaning it's also real. So it has two categories, rational and real. Most specific subset we have, though, is rational. And then finally, the very, very last one, which is 38, that is a natural counting number. So it's going to be in every single category here except irrational. So we have 5 of the 6 categories: natural, whole, integer, rational, and real. And the most specific subset it can go under is natural. If you went 10 for 10, very, very nice job. I hope this video encompassed everything that you needed for classifying real numbers. If it helped you out, leave a like on the video, comment any other topics you want to see in the future, and subscribe. Turn on that bell for post notifications. I truly appreciate any of you that watch to the very end of this video. It really means a lot. And we'll see you in the next one with some more mathematics.
The orbit that surrounds you.